next problem. Let's try plugging in infinity. See what we get. E to the 1 over x. Well, if x goes to infinity, then this little fraction is going to go to 0. So this whole thing right here is going to 1. So we have infinity times 1 minus infinity. So this is infinity minus infinity, but well, it's not L'Hopital's rulable. So this means, well, we got to do some more work. Now, you look at this, and what you want to try to do is you want to get it into a fraction so that you get 0 over 0 or infinity over infinity. And so you go, okay, well, notice that there's an x in common, and well, you could factor out an x, so let's try that. And so if we factor out an x, we would get e to the 1 over x minus 1 left over. And so you might be thinking, well, that doesn't help because I don't have a fraction. But remember, you must remember the law of the tortilla. So you have, remember when you have a complex fraction. So this is taking it back a bit. Remember that what you can do is you would multiply the very top with the very bottom, and that goes on the top. And then you multiply the inside ones, and that one's going to go on the bottom. And so this brings you a neat little idea. What if, for example, this guy, if you want to go backwards, if you want to make this guy into a fraction, what you could do is pretend like you're going backwards and bring the one that's on the numerator, bring it down on the denominator. And so what you would do, this is a handy little trick, is you would leave, let's say this one alone, e to the 1 over x minus 1, and then this would be all over, not x, but 1 over x. And so if you invert and multiply this, notice that you would get exactly the same thing. So these two are equal. But now, notice that what you get if you plug in infinity here, this one's going to 0, so this would be 1 minus 1 over, this fraction is going to 0, so this is 0 over 0, and now we can use L'Hopital's rule. So then we go, okay, L'Hopital's rule to the rescue. L'Hopital's. So then we get the derivative of the top. The derivative of e to the 1 over x. Well, let's think of e to the 1 over x. Let's think of it as e to the x to the negative 1. Because that's what it is, right? So the derivative, the derivative of this guy, well, this is going to be itself, which is e to the, let me write it like this, x to the negative 1 times the derivative of x to the negative 1. Well, that's going to be negative x to the negative 2. Okay, and then the derivative of 1 is nothing. Now, 1 over x, let's think of that as, so here, let me just rewrite what I'm talking about here. Instead of 1 over x, let's think of it as x to the negative 1. So the derivative of this guy, then, x to the negative 1, is negative x to the negative 2. Okay, now what I can do is notice I have x to the negative 2 on top and on bottom, so these guys actually just cancel. And what I end up getting is that this is equal to the limit as x goes to infinity of e to the, instead of x to the negative 1, I'm going to write it as 1 over x. And so this is equal to, well, this guy's going to 0, so this is e to the 0, which is positive 1. And that's it. We're done. Okay, so this problem is pretty tough, and so we're going to take it kind of slow. Hopefully we have enough room. But this is a different kind of indeterminate form than we've had because, well, what it is on the inside, as x goes to infinity, this inside, if you remember what we've done before is you divide numerator and denominator by the highest power, x to the highest power, and then simplify. But what we get is we get 1 on the inside. And then the exponent, though, is going to infinity. Now you might think that this is just the number 1, but you have to be careful because this guy, it's not really equal to the number 1. That's just what it's approaching. And so this entire expression could be approaching a different number than the number 1. So this is indeterminate, but it's not of the form 0 over 0 or infinity over infinity. It's not even close to being 0 over 0 or infinity over infinity. So for this, we have to bring out something that we might remember from when we were doing our derivatives, is that notice that what we have is a function being raised to another function. And if you remember back when we were getting derivatives, what we did is we used logarithmic differentiation for problems that looked like this. Now this isn't a derivative problem, but we can apply the same idea. So let's remember something. Remember that e to the natural log of y is equal to y. Now this is a property of exponentials that you learned back when you were taking algebra, and it's going to be very useful here because remember that when you have natural log of an expression, you can bring down the exponents if the expression has exponents. So what you want to do is think of this guy inside of here. Think of this guy. This is like y in this purple bubble. So what we're going to do is, instead of getting the limit as x goes to infinity of y, we're going to get the limit as x goes to infinity of natural log of y. So let me color, and so the y is going to be the purple stuff. And what we're going to do is we're going to take, so this is a sort of sidestepping, but we're going to get the limit as x goes to infinity of natural log of y. Okay, so this is equal to the limit as x goes to infinity of natural log. Now y is this stuff that's inside of the purple bubble. So this is 17x over 17x plus 7, all raised to the 7x. Okay, and then what we can do is we can bring down the exponent using the laws of logarithms. And so this is equal to the limit as x goes to infinity of 7x times the natural log of 17x over 17x plus 7. Okay. Now notice here, if you plug in infinity, what you're going to get is this guy is going to infinity, and this one, remember, the inside is going to 1, natural log of 1 is 0, so you get infinity times 0. And that's indeterminate. But here you can use the same little trick that we used in the previous problem, where we did the backwards tortilla. So this is equal to, let's just leave the 7 there. The limit as x goes to infinity of natural log of 17x over 17x plus 7 over, I forgot the 7. I'm going to leave the 7 up here because it's just a constant, so we don't really have to worry about it. But the x, I can bring it down as x to the negative 1. And then what I end up getting is, this is indeterminate, but it's of the form 0 over 0 if you plug in infinity. And so now I can use L'Hopital's rule on this guy. Okay, now I'm going to warn you that L'Hopital's rule here is going to be pretty intense. So what we have is the limit as x goes to infinity of 7. I'm just going to leave it there. Now the derivative of natural log is 1 over this whole thing times the derivative of the inside. So 1 over this guy, I don't want to write it out, but 1 over this guy is just the reciprocal. So this is 7 times the reciprocal. So that would be 7x plus 7 over, 17x plus 7 over 17x times the derivative of the inside. And here I have to use the quotient rule. So what I have is, on the denominator, 17x plus 7 all squared. And then on top I'm going to have 17 times 17x plus 7 minus 17x times 17. And sorry, it got a little bunched up there, but so that's what that is. And then on the denominator I'm going to have minus x to the minus 2. And then I have to try to simplify this whole deal. So notice that I have 17x plus 7 and 17x plus 7 squared, so I can cancel this one with one of these. And then what I get is, this is equal to the limit as x goes to infinity of 7 over 17x is this first one, times let me write out what we have here. On the bottom I have 17x plus 7. On top I'm not really going to multiply 17 times 17x. I'm just going to write it as 17 squared x. I just don't feel like taking out a calculator right now. Plus 17 times 7 That's not too bad. That's 119 minus 17 squared x. And so that's the reason why I saw this before I actually multiply these out, is that these guys actually cancel each other out, and I'm just left with 119. Okay, and then now let me write this as negative instead of x to the minus 2. I'm going to write it as 1 over x squared. Okay, so if I clean this up, I'm going to get the limit as x goes to infinity of, so here I have, if I invert and multiply this, this 1 over x squared, I'm going to have a negative 7 times 119 times x squared. So that's the 7, the 119 up here, and then the 1 over x squared. The x squared ends up on top when you invert and multiply. Okay, and then on the denominator, I'm going to have 17x times 17x plus 7. Okay, and then I can do a little simplification again. This guy cancels with this x. And what I get is this is equal to the limit as x goes to infinity of negative 833, if I multiply these out, x over 17 times 17. I guess I'll multiply it out. 17 times 17x, that's 289x plus 17 times 7, that was, I believe, 119. And now that we're pretty far advanced, we know that the limit as x goes to infinity, since the degrees are the same. Technically, I'm not supposed to do this because we're supposed to go through all the steps. But since we're pretty far in advance here, I'm gonna skip the step where you divide by x to the highest power and just say this is equal to negative 833 over 289. Okay. Now this guy, though, remember, this isn't really the answer to the question that I had. This is, if you go back, the limit as x goes to infinity of natural log of y. So if you remember, what we just found, what we have right here in our red little box here, our red little box is this guy right here. So we just found the limit as x goes to infinity of natural log of y, but what we're really looking for is y, and so, but we know that the limit as x approaches infinity of y is the same as the limit as x approaches infinity of e to the natural log of y. And so our answer in the end is going to be simply e raised to this guy that we have in our red box right here, negative 833 over 289. And if I approximate that, I get that this is, this is equal to 0.056. 002. No, 3. And ta-da, we're done. Woohoo!